Alright, so we'll begin section 13.4 in this video, which is the chain rule. Alright, so let z be equal to f of x, y, so a function of x and y, and then x be equal to g sub 1 of t, and y be equal to g sub 2 of t. So x and y are themselves functions of t. Then z equals a function, z equals f of g sub 1 of t, comma, g sub 2 of t is inherently a function of a single variable t. So although when we look at z, we look at it as a function of x and y, but if x and y themselves happen to be functions of some variable t, then that means that z really, now you only see one variable in here. The only variable you see in there is t. So it really is a function of one variable. And we have a function of one variable. We can take ordinary derivatives like the derivatives that we took in calculus 1. Is going to look a little bit different, but taking a function of one variable is what you want to think of. So thus, we may take an ordinary derivative. Ordinary in the sense we've been taking partial derivatives, and now we're going to take an ordinary derivative. It will still include us. It will still require us to have a knowledge of partial derivatives, though. So if it boils down that your function of two variables is actually just a function of one variable, then we can take an ordinary derivative, dz dt. And notice the difference in notation, d. And when I do partials, I'll avoid using the del notation. So your textbook, when you read your textbook for this, they're going to use this notation for their partials. Probably I'm not going to use that because I don't want you to think that that's this d or get them confused just based upon my handwriting on your handwriting. So I won't use that. Now, how do we find dz dt? We take the partial of z with respect to x. So you're going to take z sub x and you multiply that by the derivative of x with respect to t, plus you take the partial of z with respect to y and you multiply that by the derivative of y with respect to t. So compare this notation with the notation the textbook uses. Use whichever one's going to be easier for you to remember how to do it. And their notation, one benefit to the notation they use in the textbook is it might be easier for you to keep things in line because they're going to have an x in the denominator and you may think like things cancel. So look at their notation as well as this notation. Now, one thing to keep in mind here, when we take the partial of z with respect to x, it's going to have x's and y's in it. And when we take the partial of z with respect to y, it's going to have x's and y's in it. But notice this thing should be a function of t. So after you take your partials, this and this, you need to plug x back into this. And then you need to plug whatever your y is back into this. So your final answer should be in terms of t. So now let's talk about the scenario, a little bit more complex scenario than x is equal to a function of t and y is equal to a function of t. So now if we let z be equal to a function of x and y, x is equal to g sub 1 of u comma v, y is equal to g sub 1, g sub 2 of u comma v. So now in this scenario, then z equals f of g1 of u comma v comma g2 of u comma v is inherently a function of u and v, two variables. So now, because we're still a function of, it's still a function of two variables. Here we looked at it as a function of x and y, but we find out that x and y themselves are functions of the two variables u and v. So we take that, plug it in, and we see that z is a function of u and v in actuality. So if we have z as a function of two variables, no matter which way we look at it, then whether it's this or this, we have to take partial derivatives. Now, because inherently it's a function of u and v, we really want in the end partials with respect to u and v. So thus we must take partial derivatives. So we can't talk about an ordinary derivative here because we don't have a function of one variable. So thus we must take partial derivatives. Take partial derivatives. So now we're going to put together a little chart to try to remember how to take partial derivatives under such circumstances. Now, this is not the most general case. This is just, we're looking at two variables, but you can expand this or generalize this to three variables and beyond. We'll see three variables, and I'll do some examples with three variables, but I'm going to introduce it using just the fact that we have two variables here. So we have z initially, so we're going to make a little chart in the middle of our page. You all's textbook does this chart horizontally. I do it vertically. It doesn't matter one way or the other which way you opt to do it. So z is itself a function of initially just x and y. So x, y. But x and y, x is a function of u and v, and y, I'm trying to make sure that these two in the middle don't get too close to one another because I need some space to write. So, and y is a function of u and v. All right. So now what we want is we want the partial of z with respect to u, and we want the partial of z with respect to v. So notice if you have a function of one variable, there is only one derivative. But when you start talking about partial derivatives, it depends on how many variables you have, and that determines how many first derivatives you have. So the first partial, because z is a function of two variables, we're going to have two first partials, a partial with respect to u and a partial with respect to v. So on any individual line here, what you're going to do is just write out what particular partial that would be. So here, this would be the partial of z with respect to x. So I'll write z sub x right there. And here, this would be the partial of x with respect to u. So x sub u. Here, that's x and a v. So this would be x sub v right there. Here, this is z to y. So this is the partial of z with respect to y. Here, this is y, is a function of u. So that would be y sub u. And then this right here would be y sub v. So now, when I want the partial of z with respect to u, what I would do is I take the product of any legs that lead. I take the product of the legs that lead from z to u. So I take the product of this leg, and I add that to any other product of legs that lead to from z to u. So I'm going to add this times this plus this times this because those lead to u. And I'll write that out in words, and then I'll write out the formula as well. So to find z sub u, take the product of the partials along each path from z to u. Then add these partials. Then add these partials. That is, and I'm going to write, I'll say it here and then I'll write it on when I go to the next page. That is, z sub u is equal to z sub x times x sub u, and then plus z sub y times y sub u. So z sub u equals z sub x times x sub u plus z sub y times y sub u. And then we can do a similar thing because we also may want the partial of z with respect to v. So a similar approach. Gives us the partial of z with respect to v equals the partial of z with respect to x times the partial of x with respect to v plus the partial of z with respect to y times the partial of y with respect to v. Now, similar to when you take we were taking that ordinary derivative that I talked about earlier, this z sub v and z sub u at the end, because our function, we're saying z is inherently a function of u and v, our answer here and our answer here, they both should be in terms of u and v. You shouldn't have any more x's and y's in there because you should have plugged in your function x and y. So your final answer should be in terms of u and v. All right, so, and I'll just make a note of like to generalize this, but then we'll look at how to do this in a slightly more complicated scenario when we look at an example. So a similar chart can be formed for a function of inherently any number of variables from its chart the function's partial derivative formulas can easily be found, or can be easily found. And you can see examples. Let's see. In your textbook, they have some good examples. So see examples, I think 3 through 5 on page 850. So examples 3 through 5. On page 850. And also, while I'm pointing out some things in the book, I'm going to go back in your notes a little bit and point out which these formulas, to which problem these formulas will pertain. Also, these two that we have up here, you can go back and just put a little note next to these. So C, let's put it down here actually. So C. Now they'll change the variables in the textbook. Sometimes they'll use U and V, sometimes they'll use R and S. So don't get stuck on the fact that we had U and V here. They introduce everything in terms of U and V, but then they switch intentionally just so you understand that it doesn't have to be U and V. All right, so C, exercises 6 through 14, then 21 through 24. So 6 through 14, your function, your initial function, Z in that scenario is a function of 2 variables. In 21 through 24, your initial function, they call it W, and it's a function of 3 variables, X, Y, and Z. So 21 through 24 have a little bit higher level of complexity. And let's actually go back to the first page of our notes so I can tell you where to find some examples. If I can find the first page of the notes. So in your first page of notes, go back and write down for these problems when we had dz, the ordinary derivative. Those would be, let's see, so C, exercises 1 through 5, then 15 through 20. So 1 through 5, it's going to look exactly like this, the form that you're going to use. On 15 through 20, instead of having Z as a function of T, you have W, which is a function of X, Y, and Z, and then X, Y, and Z are functions of T. So you're going to have a third term here. You're going to have in that one, you have W sub X times dx dt plus W sub Y times dy dt plus W sub Z times dz dt in that scenario when you look at 15 through 20. All right, so I'll stop this video here, and then our next video, we'll go over some examples of these different types of derivatives we've introduced.